In this video, we will be looking at families of functions. And before we look at what they actually are, we're going to start with some familiar questions. So the first one, determine the possible equation for each polynomial function. So we're refreshing on our knowledge of the x-intercepts of a polynomial, how the behavior around those x-intercepts relates to the order or that exponent on that x-intercept bracket. So on our first polynomial function here, we have an x-intercept at -6, another one at -1/2, and another one at 3.5, which is 7/2. Now these x-intercepts, we're passing through all of them, so I know for my brackets they're all going to be in order of 1. So for the -6, it'll be x plus 6. For the other x-intercepts, we're not writing them as x plus 1/2 or x minus 7/2. That's not proper form. We have to put it into our proper format with a coefficient in front of x. So it's going to be 2x plus 1. If you struggle with how we can get that, just set x equal to your x-intercept and then cross multiply and slowly bring everything over to the other side. So if I were to cross multiply this, I would have 2x equals -1, and then bring the -1 over. And here is your bracket, because that bracket, you would set it equal to 0 to solve for the x-intercept. Same thing, 2x minus 7 for the last one. Now, the only thing that we don't really have here is the leading coefficient. I didn't put a scale on the y-axis, so we're not going to solve for it. But I do know that it should be a positive leading coefficient. So I'll just write positive a. I know it's a positive leading coefficient because we're going from quadrant 3 to quadrant 1. We have a general upwards trend, and it's an odd degree. Let's look at the next one. We have a bounce at -7, and we have a pass at +6. So my bounce means that we should have an order of 2. And then the path is just x minus 6. And this time for my leading coefficient, because I'm going from quadrant 2 to quadrant 4, I have a general downward trend. I know my leading coefficient will be negative. Next one, we have -2.5, so that's -5/2 with a pass, and then a point of inflection at +3. And this, because the end behaviors are both towards positive infinity, this is going to be an even degree and a positive leading coefficient because we are going upwards. So for the -5/2, it's going to be 2x plus 5, and then x minus 3 all cubed for that point of inflection. For the next one, we have two bounces, one at -3, one at +4. It's an even degree because we have the same end behaviors to negative infinity. And because they're going to negative, we have a negative leading coefficient as well. So x plus 3 squared for the first bounce, x minus 4 squared for the second. And the fact that when I add those exponents, I get that 4, which is an even number, it justifies my thinking about an even degree. Okay, we have a point of inflection at 0, and we have a pass at 4. Overall downwards trend, we have another negative leading coefficient for an even degree polynomial. So we have x cubed for the point of inflection at 0, and x minus 4 for the pass at 4. Why don't you try the last one on your own, and then come back to the video to check your work. So at -4, we have a pass. At -2, we have a pass. At -1, we have a pass. At 3, we have a bounce. And at 4, we have a pass. And overall downwards, so another even degree polynomial, we should have x plus 4, x plus 2, x plus 1, x minus 3 squared for the bounce, and x minus 4 for the final pass. And just a little quick check. 1, 2, 3, plus 2 is 5, 6. My degree is 6, so that's great. All right, same thing, but this time we're given words instead of a graph. So for our first one, we have a degree of 3, a double root at 4, and a root at -3. We're not told anything about end behaviors, so I don't know anything about my a value, but it says determine a possible equation. I can put whatever a value I want. I'm just going to leave it basic with a 1. A double root at 4 would mean x minus 4 squared, and a root at 3 would mean x plus 3. And that is a degree of 3 overall, so great. A degree of 4, a point of inflection at 2, so x minus 2 cubed, and a root at 5, so x minus 5. Degree 3, and the roots are given, so why don't you pause the video and come back to check your work. Here we are, nothing fancy with the roots, they were all order 1. And degree 3 starting in quadrant 2, ending in quadrant 4, so with a little visual, 2 to 4 would be a downwards trend, which means we're going to have a negative leading coefficient. And then we have a root at -2 and a double root at 3. There we are. And you try the last one, degree 4, starting in quadrant 3, ending in quadrant 4, double root at -10 and 10. And there we are. We have a negative leading coefficient because we're going down forever in both directions. So families of polynomial functions are functions that have a same characteristic. So for example, if you have a set of polynomials that all have the same x-intercepts, they belong to the same family. Now, the other points can be unique, like the y-intercept, those max and mins can differ. But if the x-intercepts are the same, they're part of the same family. If you know the equation for a family of polynomial functions, for example, if the x-intercepts are the same, you have everything except that leading coefficient, that a value, you can always solve for the equation for the specific family member using a point that is given to you on that graph, which we've done before, but we've never called it a family or a family member equation. So let's take a look at a couple examples. A family of a function has a degree of 4 with zeros at 0, 3, and -4, and we're given some information about that order. So we don't know the a value. One of the zeros is at 0, so I'll just write x. I'm not going to write x minus 0, that's excessive. X minus 3 squared and x plus 4. And it says write equations for two functions that belong to this family with different end behaviors. If I want different end behaviors, I just need my sign of the leading coefficient to be different. So for example, I could have a positive leading coefficient, whatever value I want. So this one would go from quadrant 2 to quadrant 1. Or I can give myself a negative leading coefficient so that I'm going from quadrant 3 to quadrant 4. Same family, different end behaviors, also different y-intercepts and max and mins. Now let's go specific. Determine an equation for the family member of the family that passes through the point 1, -5. Well, now that I have a point, that's an x and a y value. So I'll replace y with -5 in my general equation for the family, and I'll replace all my x's with 1. And now it's cleanup time. So a -5 equals a times 1, okay? 1 minus 3 is -2. -2 squared is 4. 1 plus 4 is 5. So that means we have -5 equals 20a. Divide both sides by 20, and you get -1/4 for your a value. So now we have one of the members of this family. And here we are. And actually, I'm just going to erase that bracket there. And there's my equation. let's try a final example. Write the equation of the family of functions that has zeros at +1 and -1 and 2 plus or minus root 3 in factored form, but with no radicals. Okay, so let's begin. Y equals A, because we're doing a family member. My zeros are plus or minus 1, so if the first 0 is at -1, here it is. The second is at +1, here it is. Now for the other one, it's a little fancier, but same thing. X minus the first value and x minus the second value. Because that's really what we did with the plus or minus 1. Like x minus 1 represented the positive version, and x plus 1 was us doing x subtract -1. So that's exactly what I'm doing with the more complicated version. So now let's clean this up because it says that we can't have radicals. My first brackets are perfectly fine the way they are, so I'm just going to rewrite them. The next ones, I'm going to clean up the bracket within a bracket by distributing the negative in. So I'll have x minus 2 minus root 3 and x minus 2 plus root 3. And if I want to get rid of that radical, I'm going to try to do some distributive property here in the hopes that those root 3's will clean up nicely and I won't have radicals anymore. So let's go ahead and do our distribution. So I'm going to distribute x first into all three terms. So that's going to be x squared minus 2x plus root 3x. I really hope that disappears at some point. Now I'll take the -2 and distribute it. So minus 2x plus 4, because I'm careful with my signs, minus 2 root 3. And now I'll take the root 3 and multiply it in. So minus root 3x plus 2 root 3 minus root 3 times root 3 is technically root 9, and the square root of 9 is 3. Perfect. At least that radical is gone. Now let's see what can clean up. The root 3x can cancel out with the negative root 3x. And the -2 root 3 cancels out with the +2 root 3. So all my radicals have canceled out. I'm just going to finish collecting my like terms. So I have x squared, -2x and -2x, 4 and -3, and there we are. Now we have the family of the function with those zeros. Radicals are gone and cleaned up, and there we go. If I wanted to find a specific a value, I would of course need a coordinate to go with it.